Hello, in this video we are talking about modular design. So we are seeing in this slide a 2-bit binary addition that takes 4 bits of input and produces 3 bits of output. In order to design this using min-term expansion approach, we need to design a circuit for each of the output bits. Therefore, we need 3 circuits. So this leads up to a very complicated circuit, and the solution is to use modular design. What does it mean to use modular design? Let's take a look at our bitwise addition algorithm. In this algorithm, we are adding the number of each columns. So we can define a full adder that adds the number for each column. This full adder needs to take x and y as the inputs of each number, and also carry in, which is represented by Cn, and also this full adder needs to produce the sum of all these columns and also carry out which is going to go to the next column for addition. So we can build a full adder by designing circuits for each of its output. It means for S and C of out. We can design this using min-term expansion. After redesigning min-term expansion circuits for S and C of out, we can build a full adder. So using the abstraction, we can represent this full adder as a black box. And with combining these black boxes together, we can build our addition circuit. So here it is an example of using 2 full adder to have a 2-bit addition circuit. So you can see here the Cin for the first adder on the right is 0, which is a default. We don't have any carry. We pass the first bit of x and y into the first full adder, and also we pass the C of out of first adder to the Cin of the second adder, and we get our 3 bits of output. So this approach is known as a 2-bit ripple carry adder, and we can build the large adder with adding more of these full adders. We can compare this approach with min-term based approach for 16-bit adder. For 16-bit adder using min-term based approach, we will need billions of gates, but for using the ripple carry adder, we only need in terms of hundreds of gates, so we save up a lot. Here it is another example of 2-bit ripple carry adder. I encourage you guys to pause the video and make sure you understand it. And also after we build a 4-bit ripple carry adder using the 2-bit using the full adders, we can consider this 4-bit ripple adder as another black box and use it in our designs. So in a problem set, you will ask to build a 4x2 multiplier, and after getting the initial results, we are needing an adder that add up to this immediate results of multiplication together. and so you need to add these partial products using a 4-bit ripple adder, and using a 4-bit ripple adder, and we can build a 4x1 multiplier, uh, and you can also, in a problem set 7, you will ask to design a 3x2 divider. This is a little bit more complicated, but you will see here the truth table on the right. For instance, when we divide 7 by 2, the result is 3, and you can see it. Also, we have a error bit as output. If the divisor is 0, the output error is 1, and the rest of the situation, the error bit is 0. So you can design this using min-term expansion. It requires you 26 ANDs and 3 OR gates, or you can use a modular design, but you will tackle this problem on the problem set 7.